So those things you already done during the class. So there's a lot of formulas for the capacitor, right? So the simplest one, you can apply Ohm's law, and then general formula for the capacitor. And then this C is actually called the capacitance measured by Farad, amount of charge measured by Coulomb, voltage across capacitor measured by volt, right? And also the capacitance, then we understand from this equation, it's look like depending on external voltage, but it is not. It actually depending on only geometric parameters. So we identify this formula epsilon 0 A over D. Epsilon 0 is actually called the permittivity constant, right? 8.85 times 10 to the negative 12. This is actually connected directly to the Coulomb constant. Okay, that's where we started everything by defining the force between the charges, right? The Coulomb force. So this K is actually 1 over 4 pi epsilon 0, which means epsilon 0 you can calculate 1 over 4 pi times K. Okay, now which mean if I have a different, because this depending on the medium, so this is actually generally called for the air, or we generally call it for free space. Free space means there's no particular medium inside there. If we have a capacitor look like two parallel plates sitting close to each other. So each plate has a connection, and then if I fill this gap with the medium called the dielectric medium, dielectric medium is a material which is not a conductor. However, that material inside molecules can polarize easily when we apply external voltage, right? So that's the idea. If I fill this medium with some sort of, this is space with some sort of dielectric medium which has a dielectric constant K. This K is the ratio between the permittivity and the permittivity of the free space. This is the permittivity of the medium. This is the permittivity of the free space. This K called the dielectric constant. That is unitless, just a number, okay? Dielectric constant, unitless, just a number. So that number also we can see how it is affecting. Now, if I fill the capacitance with the dielectric medium, this C can be written K times epsilon 0 A over D. So this part gonna be then the previous capacitance. Now this is the new capacitance, which means the dielectric constant times the capacitance of the free space or the which means if I fill the capacitor with the new dielectric medium, as a result of that, the capacitance will be increasing because this K always a constant which is larger than 1. If I have a K number 10, K number 11, or 50 or 100, depending on that, we can increase the capacitance of the capacitor. Okay, so that's the idea of the dielectric medium. Okay, question. All of these we discussed during the class. Okay, you should have a good idea about all of those things. All the formulas you can see on the theory section. And then energy storage, things like that, which is we're not going to calculate, but you can see those equations. And then keep track on this energy per unit density. I think I forgot to mention that during the class time. That's something very useful. Very end of the semester, we will discuss EM waves. When we discuss EM waves, the basic idea of EM waves is actually energy transfer from one point to another. At that point, we're gonna talk about energy density of the EM wave. At that point, this equation number 6 will show up. Okay, remember that is actually generated from the idea of capacitor. Okay, so the inside the capacitor you have electric field. So if I calculate the capacitor energy, the capacitor energy, we can write it down 3 different ways. Equation number 5, you can see that here. So if you take that equation, divide by the volume of the capacitor, then we can get equation number 6. That nothing to do with this lab, but that is something to keep that in mind, which is very important equation, very end of the semester, last chapter. Okay. So the other important aspect of this lab, we're going to take a look actually during the lab. First part, we're going to take a look the effect of this medium. For example, we're going to take a look effect of A to the capacitance, effect of D to the capacitance, and effect of dielectric medium to the capacitor. That is actually part A of the lab. Then part B of the lab, part C of the lab, this is part A and B of the lab, first table and second table. Part C, third table of the lab, we're going to take a look capacitor connection. So we can connect serially, serial connection, and also we can do parallel connection. All of this we discussed during the lab, okay? Figure number 1 and 2. Serial connection mean all should be in the same line. Parallel connection, all should be connected to the same voltage. You know, if I have a serial connection, equivalent capacitor should be inverse addition, right? Inverse addition of all the capacitance. Remember, if I have a resistor, this should be inverted, right? So if I have a parallel connection, equivalent capacitor is actually direct addition of all the capacitance, okay? So this is actually sum. Okay, now we're going to take a look this one too. So by using the simulator, this is very simple. We're going to set up the capacitor circuit serially and parallelly, and we'll take a look the effective capacitor. And you know how to calculate, then we can compare observed value with the calculated value. Okay? That's the first three part of the lab. So table number A, B, and C are actually that. Then part D is actually we're going to take a look what happened if I connect. Part D of the lab, we're going to take a look what happened if I connect the capacitor with the resistor and then connect this into an external DC voltage supply. Capacitor will start storing charges. So we're going to take a look what happened in this circuit. So the circuit can be divided into two sections, charging and discharging capacitor. Charging capacitor and then discharging capacitor. Then we're going to investigate this. Detailed proof of this equation also we're going to do during the class today. Very end of the class, chapter number 10, we're going to prove that equations too, okay? That's the plan for the lab, okay? So this part is actually the real lab which we're doing, and then the first three data tables are simply observing those behavior by using the simulation. Extremely simple, but this part is the real part. We're gonna really take the data, make the graph, and then investigate how the charging capacitor progress, how the discharging capacitor progress. Okay, question. Good, no problems. All right, then let's take a look first, first three data tables, and then we'll discuss in detail last data table in a bit, okay? So let us start from the first part. So to do the first three data table, you need this simulation. There's two type of simulation we need for today. So the first simulation is this one. You can click that. In this page should open up. Okay, initially it should be look like this. Okay, good. Anybody have any problem getting the simulation? This should run without any problem on any computer because it run on web browser, okay? Very recently, I came to know some of you have some difficulty with the computers and internet. Those things I don't know how to address really, but I think our library should have some extra laptops. Maybe you can contact them and then ask whether they have any laptops to loan. So you can loan the laptop and then keep the semester and then return back after the semester done. They had some numbers, I don't know. Beginning of the last semester, they had some 100 or so laptops to loan. I don't know whether they have any longer. And also there are some laptops available on STEM Center. So you can contact STEM director Luis Diablo and then ask him whether he have any spare laptop or tablets to borrow. So those things are freely available actually if you investigate. The resources are there, okay? And also the internet, as I remember last semester, there was a free internet for all the students in America. Let me take a look right here. You can go into these resources and then take a look. Free internet resources, this is actually a government activated initiative, I think. So all of these companies provided free internet access, high speed internet to all the students. If you have a .edu email, then you can get that service. I don't know whether they're providing at this point. They all provided that service during the spring semester when the COVID hit. Since we still in this COVID issue, I think it is still available for every student. Okay, so take a look those things. The resources are there, but you have to investigate them. If you have any difficulty, talk to the people. Tell somebody I have this issue and that issue. Then there may be a solution for that. Okay. All right. So let's continue. Okay, good. Did everybody have the simulation? Any question? Okay, so the first table, what we're going to do, we're going to investigate capacitor as a function of cross-section area and the separation between the plates, right? So let's take an Excel file and then build our table as we go along. So Excel file, table number 1. So what we're going to do, we're going to investigate. Let me share the Excel sheet. Okay, so let's build table number 1. Table 1, so we are investigating analysis of, you can name accordingly. Now you know how to name these things, tables and things like that. Analysis of capacitance. So we need column A, cross-section area. So you can name accordingly later. Okay, I'm going to just put A here and then the unit inside here. So area should be measured in unit of meter squared. Okay, make sure you have all of them properly done before you copy paste these tables. Okay, second one is a plate separation. Make sure you have to name it properly. Okay, you can't just put D there, instead of you have to name properly. Let's get a little bit of more space for each of these plate separation. And then we're going to calculate capacitance by using these numbers, and then we're going to observe that number from the simulation. Okay, so you have to name all of these. Okay, name it properly, name this column properly, name this column properly, and name this column properly. Okay, I'm not going to do all of them now. You know how to do all of those, and then you have to put the units correctly. Okay, for each of the column. Units, usually we put it inside these square brackets. Okay, and unit for plate separation should be in meters. Then capacitance, you know, we should get the unit of farad, large F, and then calculated value also unit of farad, large F, and then let's do percentage different at the end, percentage sign. Okay, and then let's go to the simulator and then let's take the data. Okay, good. Any questions so far? All right, so it is you can see when it is starting, it has 2 numbers given, right? Those are the smallest value given, but you can decrease that little bit more. The plate separation, we can start with 5 millimeters. You can see these arrows, right? Green arrows. When you click on the arrow and then go up and go down, then you can separate, you can see, you can change, right? You can change the plate separation, and also you can change the cross-section area by click and drag, right? So let's start smallest possible values. So the smallest plate separation is 5 millimeter, and the plate area is 100 millimeters square. So let's calculate that number first. These numbers given in millimeters, which mean I have to change those into the correct SI units. So the plate separation, now we have 100. So the 100 times millimeter square, which means 10, each millimeter is 10 to the power 3. So I have to multiply this by 10 to the negative 6, right? Each millimeter is 10 to the negative 3 times 2, 10 to the negative 6. Then I have the right SI unit, okay? Plate separation, 10 millimeters, 10 times 10 to the power parentheses minus 3. And these numbers, now you can see very small numbers. When you have this kind of numbers, it is always good idea to change this into scientific notation, okay? Highlight the whole table and format cells. Scientific notation, we can use maybe two decimal places for each of them. Then we have totally about 3 significant figures, all the calculated values, okay? Do that conversion, okay? Scientific notation, all of these values into scientific notation, format cell, scientific notation, 2. Now, to get the right scientific notation, here we have to do this equal sign, hit enter. Something missing here, the power. Okay. Now you can see, to get it into the right scientific notation, if you don't write it down with the scientific notation, that's okay. You can write this way, 10 times 10 to the power value and everything. But if you want to convert that notation into the right scientific notation, put the equal sign in front of that number and then hit enter. Then it automatically convert the numbers into the scientific notation, okay? And let's calculate this number first. Now you know equation for that is epsilon 0, A divided by D. Epsilon 0 is equal sign 8.85 times 10 to the power minus 12, okay? Minus 12, close parentheses, multiply by A divided by D. Hit enter, then you will get the number in scientific notation correctly. Now let's compare that. Let me copy paste that equation. I'm going to copy paste that equation here outside the table. Okay, that is CCAL, okay? Equation for CCAL. Okay, now let's take a look what's the number we're going to observe from our simulator. If you go into the simulator, then you can click on this icon right here, right-hand side, very top. It's called meters, right? Just click the capacitance, then it will show you the number what we expecting. Okay, 5 millimeters. I think yeah, so that should be 5 millimeters, not 10. Okay, we starting from there. Okay, so I'm getting 1.77 10 to the negative 13, my calculated value. Let's take a look the observed value. I'm getting 1.8 times 10 to the negative 12. That means 0.18 times 10 to the negative 12, which means 1.8 times 10 to the negative 13. So it's very close by, because it's rounding issue, right? So this is rounded into 2 decimal places. You can see your simulator given in 2 decimal places, but keep the 3 decimal places in our calculated value. That way we're going to see little bit of percentage error. That's better. So my observed value going to be now 1.8. I have to have in scientific notation, which means equal sign 1.8 times 10 to the power 10 times hat sign. Hat sign is shift and number 6, okay? And then parentheses minus 13. So I have exactly very close numbers. Now let's do percentage error. Equal sign, absolute value, parentheses, difference between these two. Close parentheses, divide by 2 parentheses, addition these two. close parentheses, divide by 2, close the outer parentheses, multiply by 100. So my percentage error is about 1.6. That's good enough. Okay, so usually we get a very large percentage error if you do this kind of thing in general lab, but this actually we can't do in the lab, right? We can't really have a capacitor and then we can't change the plate separation and things like that. This kind of lab we can't do in the lab, regular lab setting. All right, that's the equation for percentage different. Okay, these two are equations which I using for percent different calculation, and let me highlight the table too. So we're going to do this for 3 other different values. Okay. All right, question. This is the equation right here. Calculated value is epsilon 0, A divided by T, A divided by D, right? The cal is epsilon 0, E0 times A divided by D. That's the equation for parallel plate capacitor when the plates look like the square shape or rectangular shape geometry, right? So that we prove that equation during the class. So the same equation we're using here. And that's it. This one should be 100 times 10 to the power negative 6 because that's given in millimeter square. You have to convert the millimeter square into the meter square. Okay, each millimeter is 10 to the negative 3. If you have millimeter square, that means 10 to the negative 6. You multiply 100 by 10 to the negative 6, convert everything into scientific notation. Okay. All right, that's it. Then you have to do, this is a very simple calculation now. Now what we're going to do, we're going to change plate separation and then cross-section area slowly. And then we're going to calculate those numbers and then check the observed value. Let's say plate separation, how far I can go, maximum is 10, right? Let's go to 6. Plate separation is 6 millimeters. No need to be necessarily exactly 6. You can go whatever the number you can get. If it is difficult to stop at 6, you can go 6.5. That's okay. So 6.0, and then let's increase the plate separation. How far I can go? I can go to 400. So let's go each 100, right? So cross-section area, let's go to like 200. If it is difficult to stop at 200, that's okay. Try to go the closest as possible, right? So 206, that's fine. Doesn't matter, we calculating anyway, right? Equal sign, plate area, cross-section area, 206 times 10 to the power, parentheses, minus 6. That equal sign is important, otherwise you will not get the scientific notation. Or you can write this way, that is okay. If you want to write directly as a scientific notation, that's fine. 200 times 200, then at the end large E, that says the 10 to the power, then the minus 0.4. If you write that way, it will read accordingly. Okay, otherwise you write regularly like how we writing the numbers, but put the sign, this equal sign in front, then that number automatically will convert into scientific notation. Okay, now the plate separation is 6. So I can actually use the same number here, and then I can change the new number easily. Now you can see I just click and drag, and I'm going to change this 5 into 6. Then will automatically do it for me, that calculation. Now if cal, you can see you can easily do just click and drag. That's all. Then you go here and then observe the value. Observed value is 0.3 times 10 to the negative 12. 0.3 times 10 to the negative 12 mean 3.0 times 10 to the power minus 13. So I have exactly very close values. To get the percentage difference, just click and drag that column. That will calculate automatically for you. So the rest of the table is very simple. Let's do 2 more values and then continue to the next. Okay, there's no meaning doing this many numbers. You know how to do it for one, then you will gonna get the same calculation again, only the numbers are different. You can see capacitance change. Okay, that's the important thing you observing. Let's do 7 millimeter plate separation. If it is difficult to stop at 7, just take the number whatever close to 7. Okay, and the cross section area, let's do like 300. Whatever number close to 300, that's totally fine. Just get that number and then finish the calculation. Okay, I'm gonna stop here 286. So this number gonna be, what I gonna do, I gonna click this and drag, then I gonna change this number right here. So now I have 286. This number is now 286. And this number I need to change now that to 7.1. Click and drag, it will copy the same number to the bottom cell and then change that number into 7.1. Okay, 7.1. And then click and drag these 2 columns. It will automatically do the calculation for you. So the number is 3.6 times 10 to the negative 13. So this also you can do easily. Click and drag and then change the number. Click back on that cell and then change this number into 3.6. Okay, then you click and drag the last column, then that will do percentage difference for you. So that's the whole idea using the Excel. Okay, your calculation going to be very less time consuming. You can see only first line I did all the calculation in detail, and then all the rest I just click and drag this column, right? Each cell you can see this solid dot at the very edge of the right hand side bottom. When you click on any cell, then you click and drag, that will do the number or the calculation for the next line. Okay, that's all. Then you do one more time, then we can go into next section. So the next one, let's do the maximum value 10 and 400. And drag this one. This need to change now into 400. And the second one right here should be changing to 10 millimeters. And then calculated value gonna be 3.54 times 10 to the negative 13. Now let's take a look what number I have here. 3.5 times 10 to the negative 13. That's the observed value. So I have 3.5 times 10 to the negative 13. Okay, then the percentage error, click and drag. All right, so we done the table number 1. Any question? Anybody have any questions so far? Everybody okay with the table? Good, you need to name these columns properly, okay? Before we start the next section. Good, any question? So before you copy paste this table into your report, make sure you name this. This is cross section area. Let me name only for table number 1. Let's complete everything. Cross section area. This one. B7. V7 was 7.1. You may not have the same number as mine, okay? Only thing you need to check whether you observed and the calculated C values are same or not. If not, then you're doing something wrong, okay? You don't need to have necessarily my numbers. You can do any cross-section area, any plate separation, doesn't matter. But make sure after you do the calculation, these two numbers should be about the same, okay? Column C and column D should be about the same. These two, you can do any numbers you wish, doesn't matter. I just randomly select some plate separation, some cross-section area. Those are doesn't matter, okay? Good, any question? All right, make sure you name all of these correctly. This is plate separation, column number 2, column number 3, observed capacitance. Yes, take the picture and then you can include the pictures into Appendix C, or you can include even into the procedure section. If it is a detailed report, procedure section, okay? C is capacitance observed, and then column number 4 is capacitance but measured, capacitance calculated. We can say cal. Okay, make sure you name properly all of these columns before you start next table. Okay, table number 2, we're going to do same kind of observation, but only difference. The make sure every table sometime has a questions included with that, right? So you have to take a look what are the question. In this question, it says find the capacitor plate area lowest value and then increase the plate separation. Actually, that is not what we done. Okay, so this question, I think I forgot to edit that. That's okay. The table number one, this question, don't worry about that. Note down the capacitance, charge and storage. That's not what we done. We calculated everything. Let me show you. You can actually observe all of those. Energy storage, charge storage, electric field inside. All of these we can actually observe. If you apply, you can see what I am doing now. I click all of these right-hand side, and then you can see I can apply the potential into the capacitor. As soon as we apply the potential by using this battery, you can see capacitor store the charges. As soon as it store charges, you can see capacitor is actually building a potential across that. As a result, it will have electric field. As a result of that, it will store certain amount of charge. It will store certain amount of energy. We can do all of these calculation, right? We know the equation, but it's not much meaningful really. It's gonna be about the same way which we done on the previous calculation. Instead of that, we'll try to do different things. The table number 1, you can talk about this condition as a discussion, okay? So talk about little bit what's the charge storage, energy storage in the capacitor as a function of the potential applied, like couple of sentences. You don't need to write it down a lot of detail. Select the one case, like the case number 1 right here. One case, column, table number 1, first row. And then by using the information right here, you can actually calculate all the information. You know the external potential V, then you know all the equation for the charge storage, electric field, and all the information right here. Then you can do that calculation only for one case, and then discuss about it like 1 or 2 sentences. That's good enough. Okay, you don't need to do the same thing again and again for whole table. So that's not much meaningful. Get that idea? Any question? Good. That you have to do when you're doing the lab report. Okay, we're not going to spend time on that. And the potential, I can measure across capacitor by using this potentiometer. You can see if I do that, when the capacitor fully charged, that potential is equal to the potential applied, right? Potential applied is 1.5 volt. If I know the potential, if I know the capacitance C, then I can calculate amount of charge storage, right? Q equals CV. By knowing all of those information, you can see there's internal electric field. If I want, I can calculate even that value. If I know Q and V, I can calculate energy storage, okay? So all of these numbers we can observe from here, but that is not what we interested at this point. Everybody get that idea? So let me write it down that here, Q, U, and E. Check these for only row number one, okay? Row number one of the table number one. So that since you already have all the values, let me write it down. Applied voltage V is 1.5 volt. All the other information you already have here for case number one. By knowing this, you can actually calculate all of these three parameters, okay? Do that calculation, include into your report just below this table, okay? Only for row number one. Good, any question? Let's continue to table number two then. Ask any question if you have, okay? Table number two, we're gonna take a look the effect of dielectric medium. Effect of dielectric medium. Okay, so all we need is now you go into the simulator, select the second option, this option. Then you can see this extra item appear right here, right? That's the dielectric medium, okay? Change the plate separation all the way into 10 and then keep the plate cross-section area into 100, okay? Keep those two without any change and then keep the dielectric medium outside first, okay? And then let's take a look at the table number two, what it's asking first. Table number two, what it's asking is to check the capacitance as a function of dielectric medium. So we can change the medium and then we'll check how that is affecting to your capacitance. So we need the dielectric medium, column one. Dielectric medium, we're gonna check 4 different values, right? With the number and the medium, you have to write it down there. And then capacitance observed from the simulator and the capacitance calculated from the simulator. Make sure you first make sure you write it down the column name in Word and then write it down the short format. C observed. Let me space there. C calculated. Then we'll do percentage difference. And also we need the units. For each case, there's no unit for dielectric constant, right? That is K. And there's a unit for capacitance, farad. Unit for capacitance, farad. And percentage different is just percentage. Okay, question. Everybody okay? So answer this question. Previously, answer this one question just for table number one in your report. You don't need to complete that right now, okay? Okay, so let's take a look the simulator. So first one, you can see right-hand side now, the new selection tool appear right-hand side very below. It's called the dielectric. Now you can see material is custom. Dielectric constant is 5.0, right? And if you click on there, you can see you can select actually different items, right? Let us start with the Teflon. That is a real material which has a considerable dielectric effect. So which means it can polarize itself. That's the idea, right? Now you can see capacitor, we have plate separation 10, cross-section area is 100. Just click the capacitance first, right here, right-hand side, selection tool capacitance. Then you can see capacitance is 8.9 times 10 to the negative 12. That number we calculated there earlier, right? Plate separation. Let's select the previous number we calculated. That may be easier then. So the last one, plate separation is 400 and the plate separation is 10. Cross-section area is 400. Let's do this for that. A number we calculated earlier. All right, so let's do this for that. That is easier then. Now you can see number is 3.5 times 10 to the negative 13. Let us take a look the number we calculated. Yeah, 3.5 times 10 to the negative 13. We have that number correctly. So then easily we can compare with that here, right? So that's the idea. So which means calculated value we can easily do because C0 we already know, right? This number right here is for air-filled capacitor. Air-filled capacitor, that is actually we generally call the C0. So that we know. Now, which means if I filled with the dielectric medium, if we filled with K, then you know capacitance, which is equal K times the C0. Make sense? So which means to do this calculation right here, C calculation, I don't need to have A, D, and then do this detailed calculation again. So let's take this number. This is the calculated value and then multiply by K, then I can easily do this calculation. Okay, let me write it down that equation here. C cal, how we gonna do? C cal, which is equal K times C0. Now C0 is actually this number right here. That's the plan. Okay, then our calculation is actually much easier because we keeping A and D are these constant values. A is 400 times 10 to the power minus 6 because it's millimeter, and D, the plate separation is 10 times 10 to the power minus 3. So those two will fix them. Otherwise, this calculation going to take a lot of time again, and the calculation again the same thing you already done. You know how to do that. Okay, make sense? By keeping these two fixed, C0 what we are expecting is actually the number you already done earlier, 3.54 times 10 to the power minus 13. So that we already done. We're not going to do that calculation again. Okay, make sense? Anybody have any question? Good. Okay, to get the see new calculation, all I need actually K value. Okay, now we starting with the medium called the Teflon. Teflon, the K value is 2.1. Okay, so let's write it down, that name and also the number. This is Teflon. K is equal 2.1. Okay, parentheses, I write the value of K. Name of the medium is Teflon. Now let's bring that medium and then insert into the capacitor. Now you can see, keep eye on this capacitance, this green line on the top. Okay, now insert the capacitance slowly. You can see capacitor is increasing, increasing and increasing. When it is fully inserted, now you have a different number here, 7.44 times 10 to the negative 13. That's the observed value. Okay, this number now equal sign 7.44 times 10 to the power minus 13. Why I did the equal sign? Because I need scientific notation. Okay, and the calculated value equal sign K, which is 2.1 times C0 is actually number here which I highlighted in yellow color in previous table, 3.54 times 10 to the power negative 13. parentheses minus 13. Now you can see the both numbers are extremely close, right? That's what we're expecting. Let me copy paste this equation. So then C calculated is equal, I did this way, okay? That's the equation for that. Okay, good question. Now let's do this calculation to other different mediums, okay? Two other different medium. Anybody have any question? Everybody did that calculation. So the table number 2, we are not changing cross-section area, plate separation, or anything, okay? We're going to fix that number into one number from the previous table. You can fix that into any numbers from the previous table. Doesn't matter, any of the selected 2, A and D, okay? I select the last one. I select the last one because I already have that calculated value. Then by keeping that number fixed, now what we're doing, we insert in the dielectric medium in between the plates. As a result of that, we know capacitance must be increases. Now you can see if you compare these two values are very different from each other, right? This number C18, and if you compare that with the air-filled capacitor D8, those two numbers are almost twice. So that's what we're expecting. K value is 2.1. Then it's very simple. Then you do this for different dielectric medium. You click on this dielectric selection tool, change that into paper. Paper has actually higher dielectric constant, right? You can see it's 3.5. Let's change into 5. Observed value is 12.4. So it's very simple then. Now we have paper. This is what, 3.5? And then the observed value is from the simulator. 3.5, the K value, observed value of capacitance, now 12.4 times 10 to the negative 13. So you can do the same thing we done earlier, click and drag this and then edit this one. Now this is 12.4. Oh, not that one, the lower value. Click on the right cell and then edit this number. This should be 12.4 now. That's all very simple. Then to do this calculation, again, you can do the same thing. You can click and drag this downward and then edit the new value. This should be now 3.5. Okay, I have 12.39, so it close by. Then do the percentage difference, you know, again, equal sign ABS parentheses, difference between these two, one minus the other, divide by 2 parentheses, addition of these two, divide by 2, close the parentheses, multiply by 100. So that's the percentage error. Convert this also into scientific notation because we would like to have the scientific notation for all of this table because we're working with very small numbers. Okay, scientific notation with 2 decimal places. You have to change the dielectric medium here properly. If you have a different numbers, the capacitance will change automatically. And the whole dielectric medium should be inside the two plates. And also do not apply the potential or anything, okay? Keep it 0. You can see capacitance is actually changing if I bring this into a different values. You can see that is automatically should change, okay? There's nothing to do there. It's not anything we do in, it's the simulation does it for us. Okay, so let's do this for one other medium. Okay, let's do this for one other medium. So let's select the last one is the glass. You can see the glass has more higher dielectric medium than the other. Glass is not a conductor. Okay, that's what I telling yesterday and the day before that when we're doing the capacitance chapter. These are not conducting medium. Non-conducting medium, current will not pass through the medium. However, medium inside that you have molecules, those molecules, and then those atomic structure can actually polarize itself. Okay, that's what we're talking about. All right, now if I have the glass, observed value 16.65. So let's do this one glass. This is 4.7. Observed value is 6.65. Observed value here equal sign 16.65 times 10 to the power minus 13, 10 to the power minus 13, close brackets. It will automatically convert it into the right scientific notation then. Then let's click and drag this one and then edit the first number. Now that is K value. K value is 4.7. Then it will calculate automatically for you. Now do the percentage error. You click and drag this downward. It will do the percentage error automatically for you. You can see percentage error is extremely small. It is 10 to the negative 2 here. Okay. And all the calculation we have first lines we have three significant figures. So let's have one extra significant figure for our calculated value to get the right percentage error. And the last one, we have actually extra significant figure. The reason you can see we measuring up to 4 significant figures, okay? So we can leave it like that. Okay, so let me copy paste this equation too. That's a percentage error calculation for that table. So the percentage different calculation for that table look like that. Okay, so these values are actually comparable values to this cell. Okay, so we are using the value calculated earlier here. That green highlighted one is actually do this calculated values. Okay, that is right here. Green highlighted columns, the cells are important to do this column number C on table number D. Okay, table number 2. Okay, good. Any question? Okay, format properly all the tables, all the column names, things like that before you copy paste to the next your lab report. Okay, question. Everyone okay with that? Any question? Okay, then let's take a look what it asking. Air fill capacitor. Keep there's couple of question, right? Let's take a look. Keep the plate area 10, 100 millimeter square, and then 10 millimeter. Actually, we did for 400 millimeter square. Okay, you have to note that properly. Insert the dielectric medium slowly, and then calculate the capacitance after it fully inserted. Note down the capacitance, charge storage, and energy we did not did, right? So which mean like for the previous case, you have to do that for only one case. Okay, select the Teflon, only one case, and then redo the calculation for the charge and the energy only for one case. Okay, so we'll do the same thing like previously we done here. Select one case. Let's say I will write it down here. Okay. select Teflon and then calculate. You can do that later, okay? Calculate these values, calculate charge, that is large Q, and the energy, that is U, okay? Calculate those two, charge, storage, and energy for only that case, okay? For the Teflon case. V is same 1.5, okay? That's the maximum V you can apply. Maximum potential is 1.5, okay? So do that same thing you done for the previous case. You have to do this also. Okay, good. Any question? Everybody okay with that? That you can do later, okay? So they just below the table, answer that question, okay? Select one and then compare that, because you're doing that same thing for here, okay? For the previous table, you know how to do that for the new table. So the only difference is now you have to compare that numbers for the from the previous table to new table, okay? Only for one case. Okay, question? Right, then let's take a look. Charging, discharging capacitors, or the multiple capacitors. So let's take a look, table number 3. If I have multiple capacitors serially and parallelly connected, what will happen, right? So let's take a look, table number 3 on your experiment lab manual, table number 3. So you have to do multiple capacitor connection serially, parallelly. There's 4 different columns. I'm gonna show you how to do first 2, then you have to repeat that same calculation for last 2 later, okay, by yourself. So let's take a look the first 2. Now we are on table 3. What we're doing now, capacitor connection, right? So you can name it accordingly, capacitor connections, and column number 1, capacitor circuit. Capacitor circuit, the case number 1, we're doing all serial, all 1, 2, 3 serial connection of C1, C2, and then C3. Then we have to do the same thing we done earlier, capacitance observed. We're going to observe that from the simulator, and then we're going to calculate, because we know equation for the serial connection. Then we do percentage different, and then there's a new column here that say add a circuit diagram. You can copy paste the picture of circuit diagram here, okay? You can add it here, or you can leave it appendix C, that's okay, but that circuit diagram should be there, okay? Or the screenshot. So you have to have a circuit diagram, because we have different circuit for this each case, right? Circuit diagram for each case. Okay, question. Let me add another column here, because we need the unit for each case, right? So we need the unit here, farad, and unit here, farad, and the percentage sign for this one. Okay, so let's do this simulation then. So in simulator, you can see the third option called the multiple capacitors. You select that one. And then right hand side you will see a new selection tool appear, single, 2 in series, 3 in series, and then so on. We need the 3 in series, right? Just click that icon, 3 in series. You can see C1, C2, C3, all of them are same, okay? And then click on the total capacitance. That will show you the total capacitance value. That is the observed value. Then you have to calculate that. You know how to do the calculation. Let us add another line here, because we can add all the values of capacitance, right? C1 equals C2 equals C3. All of them are the same number. So the number is 1 times 10 to the negative 13. 1.00 times 10 to the power minus 13 farad. Okay, so that number also we need when you do the calculation. Okay, how to do the calculation for the series capacitance? That is inverse addition, right? Equal sign, parentheses, inverse addition of these. That means 1 over all of these values, then multiply by 3, right? So which means I can write this easily. 3 times 1 over these values. Everybody okay with that? That equation, if you don't remember, that you can find it here on your formula section, theory section, page number 2, very beginning of that. Okay, serial connection, equal capacitance is inverse addition, negative power 1. Okay, so each one is 1 times 10 to the negative 13. So which means parentheses 1 over parentheses 1 times 10 to the power parentheses minus 13, close that parentheses, close the other parentheses, then close the other parentheses. You have to be careful with number of parentheses here, right? Close the most outside parentheses, then power minus 1. Okay, then I get 3 times 10 to the negative 14. If you adding more and more serially, capacitance, effective capacitance must be smaller. Okay, that's what we observing here. Let me copy paste that equation. So I'm going to copy paste somewhere here. All right, so this is actually the C-cal for serial case. And let's take a look at the observed value, what we get. Observed value is 3.3 times 10 to the negative 14. 3.3 times 10 to the negative 14. 3.3 times, put the equal sign. 3.3 times 10 to the power, parentheses, minus 13. That will do automatically the scientific notation. To do this consistently, what we're going to do, we're going to format these cells into scientific notation and then keep like 3 or 2 decimal places for your calculated values only. Okay, for calculated values keep about like 2 decimal places, then we will get a little bit of percentage error. Okay, then let's do percentage error equal sign, ABS, parentheses, difference between these two, this minus this, close parentheses, divide 2 parentheses, addition of these two, divide by 2, close parentheses, multiply by 100. Okay, so the percentage error is about like 1.0. That because actually I purposely keeping this second decimal place, you can see, right? Otherwise, if I round this properly, percentage error will be 0 because the simulator do this calculation internally, right? So there's no way to get the percentage error, but I purposely keeping this because if you're doing this kind of work in class, we will get huge percentage error generally. This one is right here. This is the equation. Okay, that's the equation for the C-cal. And let us copy paste this one too. Percentage error calculation for this table. So that's the percentage error calculation for the new table. Okay. All right, so then after you've done the serial, make sure you take in the pictures, okay? So each case, make sure you take the pictures. All we have to do now, we are not interested in anything else. In here, what we interested is 3 in parallel. 3 in parallel mean you can see parallel means the same voltage across each capacitor, right? Now, if you have a parallel connection, you can see it is a direct addition, right? It is 3 times the each capacitor. So the observed value is 3 times 10 to the negative 13. So now let's do parallel. So it's the same thing. You can copy paste here and just add in this term parallel now. Parallel connection. And the observed value 3.0 equal sign 3.0 times 10 to the power parentheses minus 13. And then the calculated value, you know it's a direct addition, right? Equal sign 3 times, it's a direct addition of number. That means 1 times 10 to the power parentheses minus 13. So for that case, you will get the percentage error is 0. Okay. Make sense? Any questions? So this format cell, let's format that to represent only one decimal place because we can measure down to only one. Okay. But the calculated value, let's keep one more because that's how we're going to get the percentage error. Otherwise, actually, we can't have more calculated decimal places. But I'm keeping it from the table number 1 because that's the only way we can see the percentage error a little bit. Okay. Otherwise, you're going to get percentage difference is 0 for all of these calculated values. It's not really much meaningful. Okay, question. All right, so let's continue this. Take the picture of each case, okay? So what we need next is C1, C2 serial, C3 parallel. So let's take a look how to get that one. So the 2 in serial, 2 in parallel, you can see here, 2 in serial, 2 in parallel, which means C1, C2 serially connected, but C3 parallelly connected, okay? Now that's our third circuit. So the observed capacitance is 1.45 times 10 to the negative 13. So now in this case, the case number 3, we have serial C1, C2 with parallel C3. Okay, that's the next circuit. So the observed one is 1.5 equal sign 1.5 times 10 to the power minus 13. So that's the observed one. Now you have to do the calculated one. I will let you to do this calculated one and the percentage error yourself. Okay. Take a picture, write it down the observed value. Calculated one, you know how to do that. We done in class how to simplify this kind of circuit. So you have to do that yourself. Okay. And then show that work also somewhere on your appendix C. Okay, write it down somewhere. Let me add that here. Show the work of CCal in appendix C. And also I will add this one here, show all the pictures, all the pics of circuit in here or appendix C. Okay, here or appendix C. So you can add all the pictures into here, or if you don't like to add the pictures here, because when you add the pictures, this table can becomes very larger and not looks good. You can keep the table like that, get rid of last column and add the pictures into appendix. If you're doing this, write it down below the table. All the circuit diagrams are in appendix C. Okay, then I can go there and then take a look. It should be somewhere on your report. Okay. Okay, let's do the other one also. Next one is, everybody okay with that? You should be able to manage that, I guess, without any problem, okay? If you have any question later when you do calculation, always reach out, I can help with that. Last one, I need C2, C3 parallel, C1 serial. Let's see whether I can have that option here. 2 in parallel, 1 in serial. C2, C3 parallel, C1 serial, right? So that means you have to simplify that yourself. Observed capacitance is 0.67 times 10 to the negative 13. So this one now 0.67. We're not going to do the calculation. Okay, that's your job. You do that later. Now we have serial only C1 and C2 and C3 are parallel now. Okay, so this calculation you have to do yourself. Okay, you take the screenshot from your computer. If you are on Windows version, you have a screenshot button, right? That is Windows and print screen. And if you are on Mac, just Google it, screenshot Mac, screenshot Mac, then that will tell you how to do that. Okay, just Google that, see right there. So that telling you if you want to do the MacBook screenshot, so the command is actually right here. Okay. All right. So the table number 3, you have to do these calculated values yourself. Okay. We are not doing it here because you know how to do that calculation. And then check that, make sure all your work is added into your report as you're doing it later. Okay. All right. So let's continue now to the table number 4. So that is actually our real detailed lab component. If you're doing this in class, that is the real detailed lab we will be doing. Okay, so let's take a look in table number 4. What we're going to do, we're going to combine. That is our part of the class today also. At the very end, we will discuss how to set up and then analyze that in detail. But in this case, what we're going to take a look, how we're going to observe